Hello and welcome to video number 3. So this should be the last video on chapter 14, and that was my goal this week, is to get through chapter 14. I might post another video on some extra practice problem or maybe some AP practice problems, but this will get through the note guide and all of the information you should be comfortable with on chapter 14. We'll kind of see how the meeting goes and where we move forward and how we move forward. So for now, let's get started with the content. So today's content is on salts. So when you leave here, you should be comfortable being able to describe how salts affect a pH of a solution, okay? How do salts affect the acidity of a solution? Now, I know most people, when they hear the word salt, okay, think of NaCl, and that's the common, that's table salt, okay? That's what we all eat on our French fries and a lot of our food, okay? And that is a salt, but there's also, according to Arrhenius, the Arrhenius definition of an acid-base reaction, if I mix any acid, okay, here's an acid, with any base, it's going to make a salt and water. So this is one salt, this is table salt, and this is water. Okay, but I could put any acid here, and I could put any base here, and it's going to have the same thing. It's going to produce something here, some ionic compound that we call a salt and water. So we're not just going to be studying table salt, we're going to be studying anything that can be produced from mixing an acid and a base together. And what I want us to look at is, how does this affect the pH of a solution? If I don't mix the acid and the base together, what if I just add the salt to water? How is that going to affect the pH of a solution? All right. So our definition of a salt is another name for an ionic compound, okay, a metal and a nonmetal mixed together. And they can be formed by mixing an acid and a base together. They are formed by mixing an acid and a base together. So when they dissolve in water, salts dissolve in water, they break up into ions, and hopefully we're comfortable with that. So the catch is, some of these ions can affect the pH. Why? Because some of these ions are technically conjugate acids or conjugate bases. And I want us to understand why that is today. Okay? All right, so what we're going to be looking at here is hydrolysis, and this is just a key term you should be comfortable with. So anytime a substance uses water, or ions use water, and they generate H and OH, so these reactions both use water in their reactions, and they're bonding H and OH to themselves, and when they dissolve they can form H and OH. So this is just a term you're going to see occasionally. I wanted to quick introduce it and define it. Okay, so hydrolysis, when you're using water in a reaction, producing H and OH. Okay, all right. So, salts. There are, I think, going to be 3 conditions we're going to look at. So neutral solutions, acidic solutions, and basic solutions. And how do I define how to determine what a salt does to a solution? Does it make the solution neutral? Does it make the solution acidic? Or does it make the solution basic? Okay, so neutral solutions. Remember strong acids and strong bases. So if I look at a strong acid, HCl, okay? If I look at a strong acid, HCl, okay? If that reacts with water, and I think I have this reaction on the next slide, but I'm just going to talk about it here. If HCl reacts with water, okay, it produces H3O plus, hydronium, okay, H3O, that's a 3, an ugly 3, but it's a 3, H3O plus, and Cl, okay, and hopefully this equation makes sense and we're comfortable with it, okay. So if I were to identify Bronsted-Lowry conjugate acids and conjugate bases, this would be an acid. Cl would be the conjugate base. Okay. H2O would be a base, and H3O would be the conjugate acid. Okay, hopefully we're comfortable with that. So, Cl is technically a conjugate base if it's by itself. But if HCl is a strong acid, is this Cl conjugate base really strong at all? Now remember, conjugates of strong things, so conjugate bases of strong acids, and conjugate acids of strong bases are really very weak. Because in this battle for accepting hydrogen, H2O is winning because this reaction heavily favors the right side of the reaction. So Cl doesn't really matter as a conjugate base. Technically, it would be identified as a conjugate base if the question were to say identify the conjugate base. But it's such a weak conjugate base, it's not a very good conjugate base at all. So if I add Cl to a solution, it doesn't do anything. It's a conjugate base, but it's such a weak conjugate base, it's not very good at grabbing hydrogen from water. Okay, so it doesn't do anything. It has no effect on the pH of a reaction. And this is the same thing with K and Na. These are pieces of strong bases. So technically these would be conjugate acids, but they're conjugates of a strong base. Therefore, they don't really matter. So they're not good at doing their job of grabbing hydrogen, and they don't. Okay. So therefore, they don't affect the pH. And we're going to look at just a couple examples. All right, so salts that consist of anions, typically it's going to be the anion of strong acids, okay, because it's like HCl, HNO3, any of those strong acids, okay? And cations from strong bases, remember groups 1 and groups 2, calcium and lower, okay? Because typically, again, I look at the cation to determine if it's a strong base. I look at the anion to determine if it's a strong acid. All my strong acids start with H, okay? So anyway, if I have the anion of a strong acid or the cation of a strong base, it has no effect on the pH. Because it's such a weak conjugate, it does nothing. Okay? So adding NaCl to water, Na is the conjugate acid of a strong base. Cl is the conjugate base of a strong acid. Both of them do nothing. So when I add salt to water, they don't matter pH-wise, okay? They affect the boiling point and other things, but they don't matter pH-wise, okay? Because they're so weak conjugates, all right? And any of these for strong acids are going to do that. Any of these anions, and notice they all start with H, so I don't need to worry about the cation. Any of these anions for strong acids don't affect the pH. They're all such weak conjugate bases, they do nothing to the pH. And that's why it's important that you memorize these 8 strong acids, because you're going to be given questions about salts where you need to remember SO4 is part of a strong acid, therefore SO4 doesn't affect the pH, or Cl is part of a strong acid, therefore it doesn't affect the pH. And that's what today's homework is going to be on. Okay? All right. So, NaCl. NaCl, again, the Cl is a conjugate base, but it's such a weak conjugate base it doesn't matter. Therefore, it doesn't affect the pH. Na is such a weak conjugate acid, okay, from NaOH, it doesn't affect the pH as well. So if I have NaCl, I'm looking at the cation to see if it is going to be acidic. I'm looking at the anion, the negative ion, to see if it's going to be basic, okay? Neither one of these affect it. So again, cations of strong bases and anions of strong acids have no effect on the pH. All right. What about basic solutions? How can I add a salt and make it basic? So remember, if you have a weak acid, and we'll look at an example in just a minute, the conjugate of that weak acid is kind of a strong base. because that acid doesn't dissociate very well. So it actually favors the left side, okay? So it's going to favor the reactants. Okay? So it would affect the pH of a solution on its own because technically it is a base. Now, any of these anions from my strong substances, any of these 8 anions from my strong substances have no effect. So that's why I needed to remember my strong acids, okay? All right, so let's look at an example here. Now, Na, remember, is part of a strong base, so that doesn't matter. The anion is not part of a strong acid. So what does that mean? If I was looking at the acid that this would be involved in, acetic acid, and I drop that acid in water, this is the conjugate base of that acid. Now this, if I drop the acid into water, it's going to make the solution acidic, okay? But it's not going to make it that acidic, and I would have to use an ice table to do that because the reaction is not heavily favoring the right side. It's going to dissociate some, and it's going to create more H3O+, but it's not going to dissociate that much, okay? So in the battle between who's a stronger base, this versus this would actually win, okay? Because technically it is a base. Now, as you can see, I'm not adding this to water. So the water isn't going to become acidic. I'm only adding this to water. Okay, I'm only adding the conjugate base of this weak acid, which again, it's a conjugate base of a weak acid. Therefore, it's a somewhat strong base, and it has its own Kb value, okay, that I can get from the Ka value. So Na doesn't matter because it's part of a strong base, but this does. So I would want to determine the pH of a solution that contains this. So if I add this to water, this salt, okay, sodium acetate to water, it would make the solution basic. Okay? So again, Na does nothing. It's neither an acid nor a base. This is a conjugate base of a weak acid, and then water could be either. It's amphoteric. Okay, it's weak. So this conjugate base is actually a stronger base than the amphoteric water. So I could write my expression of this, the products, okay, of this base would accept a hydrogen here, okay, and become the conjugate acid, and then it would create OH. Now, how would I figure out how much it dissociates or how much hydrogen it takes from water? I would need to look at the Kb. Well, how can I get the Kb? It's either given to me, but sometimes a lot of these problems, they're going to give you the Ka, because the Ka is more readily found. It's of a weak acid. Okay? And then I can determine the Kb of the conjugate using an expression found on my equation sheet. So this equation is what would be happening here. Okay? This conjugate base, okay, reacts with water and produces the acid, the weak acid, and OH. So that's going to make the solution basic because it's producing OH. And it's going to reach equilibrium. Okay? I'm not looking at this, but I can use the Ka from this reaction to get the Kb of this reaction and figure out how much OH is produced. Well, how do I do that? On your equation sheet, you should see this expression. Okay? Ka times Kb equals Kw. So how do I get Kb if I know Ka? I take Kw, which is 1 times 10 to the negative 14th, divided by Ka, which is this. Okay? So to do that, it looks like this. Okay, I'm taking 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, and that gives me a Kb here. Now I can use this Kb, and if I had the concentration of this, I can use the Kb and the concentration of this to determine the OH concentration and then determine the pH for the salt, which would end up being basic. Okay, again, the Na, the K, any of the substances that are part of strong things, strong bases in this case, don't matter. They're just spectator ions. So that's why I no longer include the Na or the K, whatever this one was. Okay? All right, so if you have a cation from a strong base and an anion from a weak acid, the solution is basic. Okay, if you have a cation from a strong base and an anion from a weak acid, the solution is basic. Okay. So remember, if it's part of a weak acid, it's actually a base, so it's basic. Okay. All right. So let's determine the pH of something like that. So here I have a concentration of a salt. It's an ionic compound. Okay. Now, does the Na matter? No, it's part of a strong base. Does the F matter? Yes. It's part of a weak acid. So what would this solution be, you should think? Acidic or basic? Basic. Okay? F is the conjugate base of a weak acid. Now notice I'm given the Ka value of HF, the conjugate or the weak acid of this. You could say the conjugate of this. Okay? So now I want to determine the pH of this solution, and I'm going to think it's going to be basic. Okay. All right, so first I can write my equilibrium expression. Na doesn't matter. I'm just looking at F. I know it's a base, so it's accepting hydrogen. Here is my equilibrium expression. Now, how do I determine the pH of this weak base? Because that technically F is a weak base. How do you determine the pH of a weak base? Ice. Okay, so if you're going to do an ice table, remember you need a Kb value. I'm given the Ka, so in order to do this expression, I would need to take 1 times 10 to the negative 14th divided by the Ka to get the Kb. All right. So I take 1 times 10 to the negative 14th divided by the Ka, and there's my Kb. And now I can do an ice table. So here's my equilibrium expression. I fill in the concentration, and I'm solving. I'm solving for x, the same way I normally have. Okay, so I can assume x is really small and then solve. Okay, now in this case, I calculated the 5% rule. It's super small. X is super small. It doesn't matter. It's okay that I can ignore this. So this is the concentration of OH. So how do I determine the pH? Well, hopefully you can take the negative, hopefully you know that you can take the negative log of the OH and get the POH, and then take 14 minus that to get the pH. Don't forget that extra step. When you're determining the POH, you need to go one further step to determine the pH. Okay. All right. So bottom line, for any salt whose cation has neutral properties because it's part of a strong base, that's group 1 and group 2, calcium and lower, and it doesn't matter, whose anion is the conjugate base of a weak acid. So if the anion, the negative part of that ionic substance, is not part of a strong acid, the solution is going to be basic. Okay? All right, what about acidic solutions? Condition number 3. So if I have a weak acid or a conjugate acid of a weak base, the solution is going to be acidic. So this is the opposite of what we've just been saying. So Cl is part of a strong acid, so that doesn't matter. NH4 is part of is the conjugate of a weak acid, NH3. So this is a weak acid. And this is going to be the most common weak acid you deal with. I don't really see any others, or I haven't seen any others in any questions, because it gets kind of complicated when you're looking at other weak acids. Okay, but essentially, if you remember, if the cation matters, it's acidic. If the anion matters, it's basic. Okay, if neither one of them matters, it's neutral. What if both of them matter? I'll talk about that in just a minute. Okay, so anyway, NH4 is actually a conjugate acid of the weak base NH3. Okay, all right, so I'm doing the exact same thing I did on the last problem, except now I'm working with an acid. So here's my concentration of this. Here's my Kb. I would need to find the Ka. Okay, and then I'm determining the pH of a weak acid here. So what do I need to do? Ice. So I'd set up my ice table of my conjugate acid, my weak acid. And again, it's an acid, so it's donating hydrogen and creating hydronium. Okay. So now I plug in my values, 0.1, I have my ice table. I have my new Ka that I calculated from my Kb. And I am assuming X is much smaller than 0.1, and I'm solving for X. X is the hydronium ion concentration. It's super small, so again, if I did the 5% rule, it doesn't matter. Now in this case, if I take the negative log of X, that is my pH. I don't have that extra step because I'm working with a weak acid. So these things don't typically look like acids or bases, but if you know your strong acids and your strong bases, you can remember that technically they are acids or bases. And that was our goal here. All right, so here, again, if the cation matters, typically the only cation you're going to have to identify is NH4. Okay, that's going to be the common one. So if the cation matters, but the anion doesn't, because it's part of a strong acid, the solution is acidic. And these are some common examples here. NH4Cl, NH4NO3. Okay. Other things. This, you're not going to have to predict anything like this. I'm trying to find a good place for this. You're not going to have to predict anything like this, but these are other salts that can act as acidic solutions. So sometimes if you have a highly charged cation and you mix it with water, it can actually rip the hydroxide away from water, producing hydrogen and making a solution acidic. Okay, so if you have really strong, highly charged cations like aluminum, it can create these things that are called complex ions. You never have to predict anything like this, but you may see some questions that deal with reactions that contain complex ions, but you're never going to have to predict them. Okay, so this is what it looks like. Okay, I have some salt, it mixes with water, and it creates this complex ion, and in the process it becomes acidic. Again, you're never going to have to deal with anything like that. I just wanted you to be aware of that, but you may see some reactions that look a bit funky like this, where I'm creating these complex ions, where the aluminum is surrounded by water, and I'm creating an acidic solution. Okay, all right. So, and it's actually ripping the hydrogen from the water, or the OH from the water, creating that acidic solution, making it more acidic. Okay, those are called complex ions. All right. What if both of them matter? What if both of them matter? So this would make a solution acidic because it's a conjugate of a weak base. Okay, this would make the solution basic because it's the conjugate of a weak acid. Same thing here. Okay. This would make it acidic. This would make it basic. So what if both of them matter? Well, then you need to look at the K values. Whosever K is bigger makes it acidic or basic. If the Ka is bigger, it's going to be acidic. Okay. If the Ka of this is bigger, okay, or excuse me, the Ka would be here. If the Ka of this is bigger, it's going to be acidic. If the Kb of this is bigger, it's going to be basic. Okay, so you need to look at who's bigger. Is the Kb bigger? Is the Ka bigger? Okay, sometimes I would need to calculate that, and I ask you to do that on a couple homework questions. All right, so quick question. We're kind of finishing things up. Na3PO4, what would it do? This would be a common question you would see on the AP exam. Give you a second to try to answer it. So Na doesn't matter. It's part of a strong base. PO4 does. PO4 is not part of a strong acid. Okay, remember your 8 strong acids. So if it's not part of a strong acid, it must be a pretty good conjugate base, making it basic. Okay. All right. If the anion matters, it's basic. If the cation matters, it's acidic. Okay. Homework 10.4. We're going to do 2 problems. So number 1, arrange the following in order from most acidic to most basic. All right. So what I would do is kind of try to answer this on your own first. You can pause it. And then I'm going to continue and talk about this. Is kind of identify what you know about each. Okay. So KOH is a strong base. Okay. KOH is a strong base. HCl is a strong acid. Good. Then I'd cross out things that don't matter. In this case, neither one of these matter, so this should be neutral, because K is part of a strong base and Cl is part of a strong acid. Here, K doesn't matter, and here, Cl doesn't matter. Okay? So here, Cn is the conjugate of an acid, so this must be basic. Okay, if the anion matters, it's basic. And here, NH4 is the conjugate of a weak base, so this must be acidic. Okay, so that's how I kind of worked through this. So if I'm going from most acidic to most basic, starting with HCl, going here, going to neutral, then basic, and then my strong base. So it should look like this. Okay? And there's my order. All right. 10.4, number 2. Are these solutions acidic, basic, or neutral? If they are not neutral, please write the balanced chemical equation showing the reaction that makes it acidic or basic. Okay? Ka and Kb values are found in the table. For these two problems, I only need that first table, so I only have that. All right, so NaNO3, let's start with that. Na, it's part of a strong base. Doesn't matter. NO3, part of a strong acid. Doesn't matter. If they both don't matter, neutral. Letter B, Na, part of a strong base. Doesn't matter. NO2, is that part of a strong acid? No, therefore it matters. So what should this be? You should write basic. If the anion matters, it's basic. All right, so what about that balanced chemical equation? Well, I know this substance dissociates and creates this. And the Na doesn't matter, so I'm going to show that it's basic focusing on this. Well, how can I focus on this and show that it's basic? I would write my equilibrium expression. If I were to do an ice table, what would it look like? The equilibrium expression would show NO2 acting as a base, which is accepting hydrogen from water, creating HNO2 and OH. So this is what I'm asking, to practice writing those equilibrium expressions, and this should really be equilibrium here, showing how this would act as a base or an acid. Okay. Sometimes, again, they're both going to matter, so I would look at who's bigger, Ka or Kb, and that's why I gave you both tables. Quick review question. Who's stronger, HOI or HOCl? I'd pause it and see if you remember. So this was just those three things I went over earlier when we were still in the physical class. Remember, if a substance has oxygen, I would look at who is more electronegative. Okay, who is more electronegative? So whichever one is more electronegative does a better job of pulling the electrons away, making it stronger. So HOCl should be stronger. HOI is the weaker acid because HOCl has a higher electronegativity, pulling the electrons away, allowing hydrogen to leave easier. Okay, so this is kind of direct answer from the College Board that you could look at. It's just a quick question to wrap up this unit. But I'm looking at which one of these is stronger based on those three things, okay, that we talked about. Okay, so remember, if you're focusing on oxygen, the more oxygens you have, the stronger the acid. And if the substance doesn't have oxygen, the bigger the anion, the stronger the acid. So if it's just HI, that's stronger than HCl. Okay, but if it has oxygen, it's opposite. Then you do need to include electronegativity. All right. So today's goal was to get comfortable, identifying how salts affect solutions. So hopefully that went well. Your homework is to finish 10.4. So I'm also going to roll out soon tomorrow after I talk to you the AP practice problems, because that is all of chapter 14. Two more chapters left, and we're done with the material, and we can start reviewing for the AP exam. So I look forward to seeing you. That is the end of chapter 14.